Great. So good morning, everybody. How is the school going so far? Good, good. So it's really a privilege for me to be here, to be in the company of this amazing group of lecturers and this amazing group of learners. So thanks for having me. So I'll tell you guys about dark matter. And dark matter is a completely blank chapter in the book of physics. It's a chapter that is still to be written. There's nothing there, and clearly it's a field that has huge opportunity because it's up to us, but really up to you to fill up the chapter. 100 years from now, students will take intro physics, and they will know what the dark matter is, what's the elementary particle, which properties the elementary particle has, and how this property of that particle shape the universe in the way in which we observe it. So it's really a great time to be working in this field, and in my opinion, the way in which we're going to realize what the dark matter is will depend on two things. Number one will be the creativity and the ingenuity of both theorists and experimentalists. There's nothing that will substitute, thinking outside of the box and coming up with experiments, coming up with theory ideas that folks can go out there and test. But number two, we'll have to know how to go about dark matter. What's the bag of tricks that we need in order to understand what this dark matter business is about. And in my lectures, I will not talk about point number one. Okay, there's many ways in which you can enhance your creativity, in which you can become good at thinking outside the box. I'm not going to be talking about that. I'm going to be talking about the bag of tricks and the knowledge, the shoulders of the giants on which we want to walk on dark matter. So this bag of tricks consists of things that come from StatMech, statistical mechanics, things that come from particle physics and nuclear physics, things that come from GR in its application to the universe, so cosmology. And that's the stuff we'll be talking about. But before starting to have fun, let me just tell you a couple of things about myself. So my name is Profumo, and the best way to reach me is via email. So a little bit about my story. I was a normalista back in the day, and I graduated with Master of Science from Scuola Normale in 2001. I then moved on to graduate school in CISA, where I graduated with a PhD in 2004. In between the two, I went on and did some management consulting for McKinsey, but that's another story you can ask me about. I think it was very important for me to realize that no, that really was not what I wanted to do, and so I went back into physics with a lot more enthusiasm. I then went to the US, and I was briefly a postdoc at Florida State University, and then for 2 years at Caltech in 04 to 05. And then, to 07. And then in 2007, I joined the faculty at UC Santa Cruz, where I've been happy ever since. Okay, so I work on two things. One you'll hear some about, it's dark matter. And the other is what is the mechanism that causes the excess of matter over antimatter that we observe in the universe. This is called baryogenesis, and I'm especially interested in models of baryogenesis that operate at the electroweak scale, primarily because, hey, we can actually go out there and test the electroweak scale pretty well these days. And so please ask me about that. because I will not be talking about it at all in these lectures. So if I were to be teaching this class as a normal graduate class, I would ask everybody to introduce themselves. We don't have time for that. But please do come in person. My office is right next to where the secretariat is. Introduce yourselves. Science is not a sterile thing. It's a social endeavor. We got to know each other. You got to know each other. It's important to network. It's crucial. It's crucial to network. That's how we learn from each other, how we learn science. So please come, introduce yourselves, tell me what you work on, what do you think about my lectures, what do you think about dark matter. I'll be more than happy to get to know each one of you in person. But just quickly, among you guys, how many theorists do we have? Raise your hands. Oh my goodness. All right. How many experimentalists do we have? Okay, well, welcome to the two representatives of that species, which is a very important species. So how many Italians? How many Europeans non-Italian? How many non-Europeans? Okay, that's a more fair distribution of folks. Very good. So let me start with a quote that dates back to 1915, 100 years ago. Two guys you guys are familiar with, Mr. Einstein and Mr. Sommerfeld, were writing to each other. And Einstein writes to Sommerfeld the following statement: "How helpful to us is astronomy's pedantic accuracy, which I used to ridicule." Okay, so let me write down for you, pedantic accuracy. So when you use these words, you got to be very careful, especially if your wife, like in my case, is a pedantic, accurate astronomer. This is key. This is key in our field because it's through precision cosmology that we know what we know about dark matter as a particle. Okay, that we know whatever we know on dark matter comes from doing accurate precision measurements, and so that's key to what we know. It's also key to how we think we might learn more about dark matter. Okay, so it's really important as theorists, as most of you guys are, to appreciate what goes into a measurement, what a measurement means, and how you can use this accurate cosmology data to do good model building. Okay, so what has this pedantic accuracy of astronomers taught us? Well, one very important thing is how much dark matter is out there. Okay, so the density of dark matter. And we'll get to which measurements are important for this. But there's one thing that I'd like to introduce to you guys before we get into that, which is the so-called critical density of the universe, raw crit. You will have heard of it. And this critical density is a quantity that involves two other quantities. It's 3 times h0 or h0. That's the Hubble expansion parameter that you've heard of since elementary school. And just as a reminder, h0 has a value that is around 70 kilometers per second per megaparsec. Okay, 70 kilometers per second per megaparsec. All right, so it's a quantity that has the dimensions of inverse time. It's a rate, and that's its value. And Gn, of course, is another thing that you know of since first grade. It's Newton gravitational constant. So what is this number? What is the critical density? Let's have an idea of how dense the universe is. And we're going to use and go back and forth between two sets of units. One is solar masses in megaparsecs. That is the units that my wife likes. The other one is a set of units that I like, which is GeV and centimeters. Okay, so let's have a look at this number in these two sets of units. So the critical density, and I'm sure Paolo explained to you what critical means, so I'm not going to go back to that. But if there are doubts about that, we can elaborate on that. For us, it's just a constant that we're going to normalize numbers to. So in my wife's systems of units, this is 3 times 10 to the 10 solar masses per megaparsec cube. Okay, is this a big number? No, it's a teeny number. Okay, it's a very small number. Okay, how do you get a sense of that? Well, a megaparsec is a scale of the size of a cluster of galaxies. Okay, cluster is something that contains thousands of galaxies, like the Milky Way. And the Milky Way has a mass in stars that is 10 to the 10 solar masses. Contains, about 10 billion stars. The mass itself of the Milky Way is 100 times bigger. And we're talking about an object or a distance scale that contains thousands of galaxies, and that is an overdensity. So really, this is a very small number. So let's use the units that particle physicists like to get yet more of a handle on what this number is. 10 to the minus 6 GeV per centimeter cube. So what's the density of dark matter here? Who wants to volunteer a number? What's the density of dark matter here? Yes, you. It's okay. A quarter of the critical density. No, it's much bigger. It's about 1 GeV per centimeter cube. It's about 1 GeV per centimeter cube. So in a bottle like this, if you think that dark matter weighs a few GeV, there's one dark matter particle. There's one particle per bottle. So it's really small, the density here. This is 1,000,000 times smaller. Okay, so the critical density is about a factor 1,000,000 smaller than the density in a galaxy like ours. Okay, which in turn is much smaller than the density in the densest dark matter regions in galaxies like the galactic center or dwarf galaxies and so on. So the critical density is a small number. What we're going to do is we're going to measure things in units of the critical density. So we're going to ask the question, which fraction of the critical density? We know from the CMB that the universe is basically critical, is basically flat. So which fraction of the energy density of the universe is in matter, and which fraction is in baryonic matter versus dark matter? So the name of the game will be to measure the matter density, the overall matter density, subtract off the baryonic density, and get whatever is left. Okay, so here's the algorithm. Number 1, measure a quantity I will indicate with omega m, which is the density of matter divided by this critical density. Step number 2 will be to measure the baryonic density. Okay, so again, rho b over rho critical. And then number 3 is going to be a very complicated mathematical operation. Okay, take the difference. And this is what we're going to call omega dark matter. So the way in which you measure the overall matter density of the universe, there's a variety of ways to do number 1. But historically, if you think back about all the stories about Fritz Zwicky and his weird faces, there's this picture of Fritz Zwicky to look like this that everybody posts when they talk about dark matter. He was basically measuring mass to light ratios of clusters of galaxies. Okay, and in fact, this is a very measurement to make, and then Vera Rubin started measuring, her story, the rotation curves of galaxies, which is a way to get information on how much overall matter there is within a certain radius, etc., etc. Essentially, all of these measurements are measurements of the mass to light ratio, as a function of the size of an object. So you've got a bunch of data that kind of look like this as a function of the scale of objects, but then from some scale on, and this scale is about a fraction of roughly 1 megaparsec, this mass to light ratio saturates to a constant, and therefore what you do is you say, okay, well, this constant will trace the overall mass to light ratio in the universe, and this constant saturates at a value of omega matter that is about 0.3. Okay, so about a third of that already small number from these measurements of matter over light gives you roughly an idea that omega matter should be 0.3. Slightly more indirect way to measure omega matter in the universe is to use the so-called matter power spectrum, which is different from Montepaschi di Siena. And this matter power spectrum is essentially the Fourier transform of the two-point correlation function. So you take a measurement of where structure is in the universe. You take very large pictures of the universe, and you just count. You essentially make a measurement of the two-point correlation function and take the Fourier transform of that. Okay, so in practice, that's what you do. You have an overdensity. Okay, and then you Fourier transform it, and so you write this, and this guy is normalized in some way what people measure when they take these big surveys like Sloan Digital Sky Survey. So this P of k is also the Fourier transform of the two-point correlation function. Okay, so this P of k tells you roughly as a function of wave number or a scale how much structure there is in the universe. And so you have a bunch of data like this. Okay, this is your P of k. And what you do is you have a model where you put matter in the universe and you let it gravitationally interact, and you make predictions for how matter clumps as a function of scale. And so you can directly confront your theory predictions with data. There's also ways to do that exercise mathematically, at least in some regime. And so, for different values of omega matter, you get different predictions. And the one that works with data is, again, about 30% of the critical density. Okay, so you use this matter power spectrum to test for omega matter. And then, of course, there is the cosmic microwave background that is also a measure, in some sense, of the clumpiness of dark matter at a particular point in the history of the universe, which is a recombination. So when photons stopped talking to baryons and electrons, and so you take a snapshot of how clumpy the universe was there, you look at the anisotropy power spectrum, and that power spectrum depends on how much matter you have in the universe, obviously. And so to roughly give you an idea, you've seen this picture many times. So what happens, for example, to the first acoustic peak when you increase omega matter is this. So the acoustic peak shifts to the left. Remember, this is L, which is inversely proportional to angular scales. So what happens to the acoustic peak as you increase the matter density in the universe is that it happens on larger angular scales, and you have a smaller peak. Okay, so that's what happens. And again, there are codes that do that exercise for you in great detail. And so by comparing measurements of density perturbations at this very high redshift 1100, okay, z of 1100 is the redshift at which CMB decouples. You handle on omega matter. Again, this is increasing omega matter. So there's these three ways: mass over light. Again, you, for example, observe structures at X-rays and in the optical, and you have ways to measure both mass and light, or you take rotation curves and blah blah. There's a variety of ways in which you put down these numbers, and looking at the mass to light ratio at very large scales gives you a first handle on omega matter. The matter power spectrum, again, the Fourier transform of the two-point correlation function of structure in the universe. And number three, the CMB, essentially the first acoustic peak, really, it's what contains information on omega matter. Okay, great. So we know that of this already small number, about a third is in matter, is in stuff that behaves cosmologically like matter. So that's one first piece of information. Number two, how do we measure how many baryons there are? Well, the first and most beautiful way to measure how many baryons are around is Big Bang. So you get with the notion that light metals, astronomers call metal anything that is not hydrogen, which is very interesting to me. Anyways, light elemental abundances are dominated by their production in the very early universe. As you know, heavier metals, heavier elements are synthesized in stars. But the light ones, things like helium, helium-4, lithium-7, and so on, are mostly produced primordially, so in the very early universe. And if you know the relevant network of cross-sections and production paths for a given element, you can predict, for example, how much helium-4 you produce if there is a certain density of baryons in the universe. And the fascinating thing is that this prediction only depends on that parameter, on the density of baryons. So you just have a prediction as a continuum as a function of one single number. Okay, but then your astronomy, your pedantic and accurate astronomers measure helium-4, and so that gives you some interval for rho baryons. The same thing you can do, for example, for deuterium, for helium-3, lithium-7, and so on, and you have other predictions, and this pinpoint some range, some value for rho baryons, which normalized to the critical value is about 0.04. Okay, and it's actually pretty accurately measured, and there's some subtleties to this story. For example, lithium-7 is a little bit offset, doesn't quite work, but lithium-7 also comes from stars and can be destroyed in stars. So there's some moving parts, but more or less it's a coherent picture. And let me emphasize one important aspect of this coherent picture. So these calculations essentially rely on two ingredients. They rely on nuclear physics cross-sections and on the notion that we know how to do statistical mechanics in an expanding universe. Okay. And this stuff happens very, very early on. Who knows roughly at which time? What is the time scale for BBN? 1 second. Very well. So that's what we have in mind. 1 second, or about 1 MeV, is the scale of BBN. Okay, so the fact that we have a coherent picture for the relative abundances of light elements tells us that our crazy extrapolations on what happened in the universe essentially work very well all the way back to 1 second. So this is already an important piece of information for those of us who do crazy theory model building, because you got to make sure that you don't screw up the history of the universe at least up to 1 second. Okay, no crazy decaying particles, no crazy energy injection, no crazy expansion rates. Everything has to pretty much be as in standard cosmological models all the way back to 1 second. Okay, very important for model building. It's it's a rough thing, but up to 1 MeV things must be standard. Okay, you can go crazy for smaller times and higher energies, but you gotta be pretty conservative from that point on. So the fact that this works has historically been a guideline to how we think about dark matter. Okay, so how we think about dark matter is essentially, well, we particle physics and physics and StatMech way back in the history of the universe, and hopefully things will work. Okay, later today we're going to see this story of the freeze out of dark matter, the thermal production of dark matter. That's the same thing. And we go crazy about it. We really like it because this is such a successful paradigm for Big Bang nucleosynthesis. Okay, that's the very reason why people have been banging their head and trying to find WIMPs all over. And it's as simple as this: because BBN works, because it's a predictive theory that is just beautifully in accordance with observations. So there's other ways in which you can measure the baryonic density. Chiefly, these ways have to do with CMB. And so you have, again, your peaks, your acoustic peaks in CMB that I believe Paolo told you everything about. And if he hasn't, you should know something about. So what happens as you dial omega baryons up and down? Well, pretty much what happens is this. If you have a low omega baryon, you tend to suppress the first peak and enhance the second peak. And there's really no immediate way to see that I know of. You kind of have to work a little bit hard on understanding what the first and the second acoustic peak have to do with omega baryons. But if you work just that little bit harder, you can figure that out. So the ratio of the first two acoustic peaks and also the location is a very sensitive probe of omega baryons. And amazingly enough, it agrees very well with this probe. So this happens when the universe was much, much older than 1 second. Okay. Amazingly, it gives the same outcome for omega baryons. You can also use P of K. Again, you move the baryonic density, and as you can imagine, you affect how structure clumps, and so you affect the two-point function, and so you affect its Fourier transform. And again, this is something that is in concordance. There's also ways that I will not say pretty much anything about to measure directly the ratio of omega matter to omega baryons. And these ways are, for example, using X-ray data plus the so-called Zunayev-Zeldovich effect. So the Zunayev-Zeldovich effect, as you know, is the notion that CMB photons are affected by traveling through the gravitational potential of clusters. But how do you measure the gravitational potential of clusters? With X-rays, because X-rays are the thermal emission of gas within clusters, and so they have to do with how much matter is there. Using both of those things measures quite accurately the ratio of omega matter and omega baryons. And there's even another really cool way that my wife really likes, baryon acoustic oscillations. And that also is sensitive to the ratio of omega matter and omega baryons. So there's a variety of ways in which you can check for kind of the concordance of these very disparate measurements of omega matter and omega baryons. But the bottom line is that there is some sort of baryonic matter that really dominates the matter density of the universe. So let's now go to number 3, the important arithmetic operation, omega matter minus omega baryon, that gives you that the dark matter is roughly 1/4 of the critical density. Okay, so that's the name of the game. That's the name of the game. And it's great, but you can say, all right, I'm not really convinced that I need these new non-baryonic species. You know, I just don't understand cosmology well enough. Is there a more direct way to convince me that there ought to be stuff that is non-baryonic to explain how the universe looks like? And yes, there is. And this is an argument that is very elegant and literally one line long, that shows that modified gravity cannot work to explain the universe as we observe it. You do need dark matter. And this argument has to do with structure formation. Okay, so how do structures form? We know that the universe is very nonlinear, so these overdensities are very large. Okay, we saw that, for example, a galaxy like our own has an overdensity of 10 to the 6. Okay, so the universe has to go nonlinear. You have to have density fluctuations large enough so that things collapse and the overdensities explode. Okay, we are very nonlinear objects. There's one simple prediction that cosmological models make for how these overdensities grow with redshift. And this prediction is that the growth of overdensities roughly goes like the scale factor, okay, for matter. Okay, in the linear regime, that's always true. But this is a quantity that is constrained by this photograph. We know how large overdensities are because we know how large overdensities were back at recombination. Okay, so when baryons and photons were tied together, the overdensities of baryons and photons traced each other in a very predictable way. So we know what delta rho over rho at recombination was, and we know that this number was smaller than a part in 10 to the 4. Okay, the CMB sky is very homogeneous. Its inhomogeneities are at most of 1 part in 10 to the 4. But we also know what the redshift is, and therefore delta rho over rho today must be smaller than the redshift of recombination times 10 to the minus 4. But the redshift for recombination is roughly 10 to the 3. Okay? This is 1100. So what are we looking at? We're looking at a situation where if you only have baryons, you just cannot clump things so that they go nonlinear. You don't have enough time. You don't form structures. So what you need is this number to be much bigger than 10 to the minus 4 recombination. How do you do that? Well, if you have a species that is dark. If you have a species that is dark, it starts clumping gravitationally much earlier because it doesn't talk to photons. So it goes out of equilibrium with photons much earlier. Therefore, at recombination, this is a much bigger number, maybe already of order 1 for some dark matter models. And therefore, you have all the time in the world to go crazy and go nonlinear enough. Okay. So that is kind of, the quantitative picture. Qualitatively, the way in which I think about it is that if you have baryons and photons, baryons are charged particles. Okay, baryons are charged particles, and so they have some radiation pressure that prevents them from collapsing. Okay, it's very hard to form stars because you have this radiation pressure. So what you need is some gravitational potential, well, this delta rho over rho dark matter, that is large enough so as to beat the radiation pressure and start forming stars. Okay, that's kind of the intuitive picture that I have. And quantitatively, that's how you look at it. So yes, we do need dark matter to have timely structure formation. Okay, so dark matter is essential for timely structure formation. And so, if you do calculations more accurately, for example, for this matter power spectrum in the linear regime times k cube, what you have is, for a dark matter model, something like this. If you don't have dark matter, you have a matter power spectrum that looks like that. Okay, so this is baryons only. So you have a bunch of acoustic peaks, but you never go nonlinear. You always fall short to have large enough overdensities. So you do, for example, you guys have heard of Tevis or these modified gravity theories that you may be even able to write down in a covariant way. Well, they always fall short of predicting the correct matter power spectrum. Some of them, if you really stretch them, can go nonlinear, but they go nonlinear at completely wrong scales. The predictions for the detailed shape of the matter power spectrum are wrong in modified theories of gravity. So I would just not entertain that possibility and go with the notion that we do need non-baryonic dark matter. So there's one possibility that people have been excited in the past, and which is that maybe the dark matter is actually disguised baryons that cosmologically don't look like baryons. So let's talk about it a little bit. So how can you disguise baryons? How can you make baryonic matter just not look like baryonic matter? For example, not touching the predictions of BBN or not affecting the CMB. Well, one way is if very early on your baryons had collapsed and formed black holes, and black holes certainly don't behave like baryonic matter. Okay, so that's one interesting idea that people have put forward. So let me just write down and discuss very quickly a few possibilities for disguised baryons as dark matter. So we said one is primordial black holes very early on in the universe, where very early on basically means, a little bit before BBN. Baryons collapse, they form black holes. We don't know which mass these black holes are at. It doesn't matter, really. Can we test this possibility? And the answer is yes. There are a variety of constraints on the ratio of abundance of primordial black holes to the abundance of dark matter. And that ratio has to be much, much smaller than 1. Roughly speaking, the way in which you test for primordial black holes are microlensing events, which is this very boring exercise of staring at a star and wait for a black hole to pass by. Literally, they do it that way. Again, pedantic astronomers. But in that way, we know that primordial black holes cannot be too big. What if they're small? Well, if they're small, then there's a lot of them if they're the dark matter. But if there are a lot of them, what happens is that you have a neutron star and you have this primordial black hole that gets captured by the neutron star. Neutron star is a very dense object. And so as soon as it captures the black hole, it becomes a very big a little bit bigger black hole, and it disappears. So the trick is to look for neutron stars where there's a lot of dark matter and just see neutron stars there. Okay? So you look for environments that have a lot of neutron stars and a lot of dark matter, and you can set very good constraints on small primordial black holes. Okay? So again, you look at dense dark matter neutron star environments. Example, the galactic center, or example, the Large Magellanic Cloud. Okay, we observe neutron stars there. We observe all the neutron stars there, and therefore we can set limits on primordial black holes that are small, so that there's a lot of them. There's a couple more possibilities. One is matchas. Okay, matchas are sort of the more or less exotic version of primordial black holes. They're like Jupiters, microscopic objects that fail to form stars that may be wandering around the halo. Well, that doesn't work also because of microlensing, so they were ruled out a long time ago. But there's a second, slightly more exotic possibility that I think is still open, and this, as many things in theoretical physics, is a possibility that was envisioned by Ed Witten. And so he said, okay, suppose that the QCD phase transition is really weird, and that maybe you can form macroscopic objects, where macroscopic is 10 to the 20 or 10 to the 30 baryons in one nugget of baryons, and maybe that's the dark matter. Okay, and it turns out that that's actually a possibility. Okay, that actually is a possibility. But even more, for me, interested in baryogenesis, that's a possibility that might have to do with baryogenesis. And you guys have all heard about asymmetric dark matter. I won't say much about asymmetric dark matter, but the notion is that in fact there is no asymmetry, and that the dark matter sector eats up the baryon asymmetry in some way. Okay, so overall there's no violation, macroscopic violation of any baryon number. The dark matter has some sort of baryon number, and it's because of this compensation of the asymmetry that that works out. So in this context, what you can have is strangelets and anti-strangelets, and people have come up with a mechanism that through the QCD theta term that embeds a little bit of CP violation, distinguishes between nuggets and anti-nuggets of baryons. There might be an excess of anti-nuggets over nuggets, and that could naturally arise and could explain the baryon asymmetry and dark matter at the same time. So this requires about 10 to the 25 baryons strangelets, and again the notion is that there is an asymmetry between anti-nuggets and nuggets that hides the baryon asymmetry. So that's still a possibility. There are ways to test it, because these nuggets, for example, would shoot through the Earth and would literally create a hole through the Earth, which we might have seen or might not have seen. So there are constraints, but there's space in the parameter space of this scenario that works. So okay, so that might be a possibility. But barring this type of constructions, it is fair to say that the dark matter is no baryonic new particle. Okay, and I'm going to go through why new particle that we need to come up with. So there's one more thing that this matter power spectrum tells you, which is that at small scales, large wave numbers, there's a bit of structure in the universe. And this informs you on how relativistic dark matter might be, because of course, if dark matter moves fast, it suppresses small scales. And this is the old story of hot dark matter. If you think that dark matter is a hot species, for example, a neutrino, then what happens is you predict a power spectrum and it works very well, then shuts off at small scales at, in fact, a wave number that corresponds to the free streaming length of this relativistically moving particle. So that's how we know that neutrinos cannot be the dominant dark matter species, and we're going to go back to that. But that is important because at this point we are ready to state that dark matter is a new particle. So dark matter is not in the standard model of particle physics. Okay, what do we have in the standard model of particle physics? We have matter fermions of two types, quarks. They certainly cannot work, barring this crazy scenario here. Charged leptons cannot work. They're charged. Neutrinos, we just said, don't quite work because of the way in which structure would form at small scales. And dark matter has to be long-lived. Certainly cannot be a massive gauge boson, cannot be the Higgs boson, and cannot be the 750 GeV particle that we might have observed, unlike some of the very early papers that excited people wrote one day after. Anyways, so there just isn't anything that in of dark matter within the standard model of particle physics. So we need a new non-baryonic particle. What do we know about this new particle? What do we know about this new particle? So let's talk about the gross features of dark matter as a particle. What do we know about it? So we talked about cosmology. Cosmology informs us about how much dark matter is there, the abundance of dark matter. So we'd like a particle physics model that does not overpredict or underpredict the abundance of dark matter. So Ryan, number one, the abundance is a good probe of dark matter as a particle if we have a consistent framework to calculate it. Also, we know how dark matter is distributed across a pretty wide range of scales. So let me write P of K. And roughly speaking, the range of scales where we know what dark matter halos look like ranges between the smallest galaxies we observe, which are dwarf galaxies. Who knows what's galaxy? 10 to the 8 solar masses. So 10 to the 8 in units of solar masses, all the way up to the mass of a cluster of galaxies, which is 10 to the 15, about 1,000 times the mass of a Milky Way, which is 10 to the 12. Okay. So within that range of scales, of mass scales, we know what dark matter halos look like because we have direct measurements of the dark matter content and the profile of this. But essentially, what we really know is the distribution of matter at a macroscopic scale. Dark matter has to be dark. Okay? So what does that mean? Well, it means that it cannot screw up this argument. It cannot talk to photons enough for it to be, for example, in equilibrium with photons at recombination. This doesn't mean that it has to have exactly zero electric charge. It's going to be a statement on how big or how electrically neutral the dark matter has to be. Okay? So really what this is some constraints on the charge of the particle, and you can imagine that is going to be a constraint that also has to do with the mass of the dark matter. So the darkness of dark matter on quantitative ground is a statement about, you know, how electrically charged it is with respect to its mass. Okay, there are beautiful plots that quantitatively tell you what the constraints look like. There's one important thing that comes out of the fact that dark matter has to be mostly dark, and it is that dark matter cannot cool by emitting photons. Okay, that is important in the way in which dark matter, for example, shapes halos of galaxies. Dark matter cannot cool through photons. Okay, so dark matter doesn't accrete on black holes, for example. The way in which ordinary matter accretes on black hole is because it spits out photons. Okay, dark matter doesn't do that, and so unless you're really, really lucky and your dark matter orbit falls within the Schwarzschild radius, you don't accrete dark matter because it's dissipationless. Okay, cannot lose photons. Now you can come to me and say, well, maybe there are dark photons and I can dissipate through dark photons. And it's okay as long as your dark photons don't mess up my cosmology. All right? So dark matter is dark, and as a result, it's also dissipationless. Dark matter is mostly collisionless. Okay, you've all heard about the bullet cluster. You've heard of that, and what the bullet cluster goes to show is that the self-interaction of dark matter is small. Dark matter really doesn't talk to each other much. In fact, that's not at all true. It's not at all true as long as what we mean by strong interactions is a strong interaction. Okay, so we all would agree that strong interactions are pretty strong. Okay, well, the bullet cluster essentially says dark matter cannot be strongly interacting, or actually it can almost be strongly interacting and it's fine. So that's the level at which we know that dark matter is collisionless. Okay. Let's put it on some quantitative grounds. Okay, so what's the typical cross-section of strong interactions in centimeters squared? There's one word that turns out was put around in 1945 by U.S. scientists working on the nuclear bomb. It's the barn. Okay, the barn comes from the fact that people were like, well, you know, it's so big, the interaction cross-section of strong interactions, that it's almost like hitting a barn with your baseball. So, you know, you throw a baseball, and if you really suck like me at playing baseball, at least you're gonna hit a barn, you know. So that's where the word barn. It's a very large cross section. One barn is about 10 to the minus 24 centimeters squared, and of course the mass scale is the GeV. So let's look at what we know about the collisionlessness of dark matter. Well, we know that on megaparsec scales, and for the typical densities of clusters of galaxies, there are no interactions. Okay, so what we know is that the mean free path of the dark matter has to be roughly bigger than 1 megaparsec, okay, for densities that, again, let me stick in the typical density of dark matter in our galaxy, so 1 GeV per centimeter cube, or about a particle per water bottle. Okay, so 1 GeV per centimeter cube. So what's the mean free path? The mean free path is, remember, 1 over number density times cross-section, right? So lambda is 1 over n times sigma from your intro nuclear or particle physics. So let's stick in numbers. N, the number density, is the matter density divided by the mass of the particle. Okay? So we want lambda to be greater than 1 megaparsec. Let me write lambda as 1 over n, which is rho over m, times sigma. Okay, this has to be greater than 1 megaparsec. So really what I'm constraining is sigma over m. Okay, let's take sigma over m. Sigma over m must be less or equal than 1 over 1 megaparsec times rho. Okay, so now we got to put in numbers. And all right, parsec. We're going to use parsecs a lot. How big is a parsec in centimeters? You guys gotta know these numbers. 3 times 10 to the 18. Magic number is 10 to the 18. Okay, so 1 parsec is 3 times 10 to the 18 centimeters. So 1 megaparsec is 3 times 10 to the 24. Okay. 3 times 10 to the 24. And then we have 1 GV per centimeter cube. And now, because you see that, let me go here. You see that if you measure sigma in units of 10 to the minus 24 centimeters squared, and if you measure the mass in 1 GeV, the mass of a proton, you get that that has to be less than 1. Okay? Which means that the bullet cluster is a statement about dark matter being, at the most, a strongly interacting particle. So you be the judge whether or not that's, collisionless. Dark matter can be self-interacting quite a bit, all the way up to strong interactions. Okay? So that's an important thing, because it also tells you that if you want to affect the way in which halos look like by the properties of dark matter as a particle, then you have to work pretty hard. Okay, these self-interacting dark matter models that you guys have heard of are things that self-interact a lot. Okay, because they affect structures in a measurable way, and to affect structures in a measurable way, this is the range of cross-sections over mass. Okay, in fact, it's not easy to build models of strongly interacting dark matter or self-interacting dark matter that works to solve, say, the small-scale structural problem. But that's how you do the rough, blackboard estimate. Okay, great. So dark matter has to be collisionless to that level. Feature number 4. Dark matter has to be essentially classical. What do I mean by that? Well, I mean that the quantum nature of dark matter as a particle really shouldn't get in the way. Okay? So let me be more specific about this statement. So imagine dark matter was a very, very light boson. Very, very light boson. And imagine that its de Broglie wavelength was big enough that dark matter could not confine on the scale of dwarf galaxies. Well, that doesn't work. Okay, because we observe halos at dwarf galaxy scales. So at most, dark matter can have a de Broglie wavelength that is as big as this number, which you can convert into a distance scale. Okay. So at most, your lambda dark matter, which is this, without the bar, which is that, it's Planck constant divided by the momentum of dark matter. What's the momentum of dark matter? It's mass times the typical velocity. Okay, you take a galaxy. I'm going to ask you guys a lot of questions. What's the typical velocity of a dark matter particle in our galaxy? Beautiful. Thank you so much. Okay, so roughly 200 kilometers per second. That's the number we sort of have in mind. Again, let's plug in the number. We all know h, so I'm just going to quote the results. The dark matter de Broglie wavelength is about 3 millimeters. About 3 millimeters if the dark matter has a mass of 1 electron volt. Is about 3 millimeters if the dark matter has a mass of 1 electron volt. So how small can the dark matter mass be? Well, the typical size of our Milky Way is 10 kiloparsec. We have learned what 10 kiloparsecs means in centimeters. So 10 kiloparsecs is about 10 to the 22 centimeters. Okay, so we want 10 to the 22 centimeters be much bigger than the de Broglie wavelength of dark matter, which let me call this, let's call this 10 millimeters. So it's just 1 centimeter. Okay, 1 eV. I borrowed the 3 from that 3, divided by the mass, which means that the mass of the dark matter has to be much bigger than 10 to the minus 22 eV. That is what classical means. Okay, dark matter cannot be arbitrarily light, because otherwise its quantum nature would get in the way. Okay, otherwise its de Broglie wavelength would be larger than the size of halos we observe. Okay, actually you can do much better than this if the dark matter is a fermion. Because if it is a fermion, then StatMech teaches us that there is Fermi or Pauli blocking constraint on the phase space density. Okay, the phase space density cannot be arbitrarily large. In fact, it has to be essentially smaller than h cube. Right? You remember that. That's Pauli block. So, but the phase space density is something that my wife goes out there and measures from astronomical data. Okay, because it's a statement about, am I out of time? Okay. Because it's a statement about, let me just finish this and then we're going to call it a day. So if it's a fermion, then the phase space density has to be smaller than h to the minus 3. Phase space density. There's actually a little number that has to do with the internal degrees of freedom, but for our estimate it doesn't matter. So I'm going to leave this as an exercise, but suppose again that you have a physical density rho that is about 1 GeV per centimeter cube. Okay, this is mass times density. So that's the physical density you use for your calculation of phase space. And again, let's use a sigma, a velocity dispersion that is a tracer of, your phase space density in velocity or momentum space that is about 100 kilometers per second. So it's used as a proxy of phase space density in momentum space, just this times the mass cube. And I will leave you the exercise of finding how small the dark matter can possibly be such that you don't violate this, okay, given these two numbers. And it turns out that the magic number is mass has to be much bigger than about 30 electron volts. Okay, but please do the little exercise and get some practice with all those numbers. You're going to get a constraint on m to the 4th, and that constraint translates into something that is about 22 orders of, or 23 orders of magnitude more stringent than for the bosonic case. All right, so we're going to cut it off here, and we're going to start the next lecture by looking at the upper limit on a dark matter mass, which turns out to be 10 to the 3 solar masses. Solar mass is very big in GeV. It's 10 to the 57. So the bottom line is we've got a lot of room to play, a lot of fun to have. I'll see you guys tomorrow at 3 p.m. There's been a change in the schedule, so the dark matter lecture will be at 3 p.m. Thank you. Oh, ancora mezz'ora, giusto. Ah. Thanks. You guys are too quiet. Very good. Very good. No. I want to go on. Fantastic. I thought 12:30. I'm sorry. I have little kids, so I have dinner at 5 p.m. and lunch 2 hours ago. Okay. So beautiful. So you can do this exercise. I won't do it for you. I won't spoil the fun. But now we have. Okay, I'm sorry. I'm gonna start erasing. This blackboard is too small. Fantastic. So what's the upper limit? Well, the upper limit comes from the fact that dark matter has to essentially be, again, I'm gonna abuse my vocabulary and use the term fluid. Okay, what does it mean? Well, it means that dark matter cannot be big clumps of stuff. Okay, cannot behave like a collection of massive objects, because massive objects are very big perturbers. Okay, there's some really neat calculations of, suppose you have a globular cluster, a collection of stars. If the dark matter is a super heavy thing that flies through, you would disrupt globular clusters. Also, you would do damage to things like, this is my very pretty representation of the Milky Way. The Milky Way has a disk, and this disk literally looks like a disk. It's a thin distribution of stars and gas. If you have very massive dark matter particles that populate the dark matter halo, what happens is they would shoot through and they would perturb the disk. They would start doing wobbly things like this, and eventually not look like a disk anymore. So you can literally sit down and estimate how big the dark matter has to be in order to perturb the disk, or in order to disrupt globular clusters on time scales of the age of the globular cluster. And the limit you have is that the dark matter mass has to be smaller than about 10 to the 3 solar masses. And again, I promised you that we were going to understand everything about orders of magnitude. So a solar mass is roughly 10 to the 58 GeV. Okay, you can convince yourself of that by thinking about how much the sun weighs in kilograms and how many kilograms there are in a GeV, or vice versa, how many GeV there are in a kilogram. So again, I'll leave it to you as an exercise. 10 to the 58 means that this is roughly 10 to the 61 GeV, which is 10 to the 70 electron volts. Okay, so bottom line, mass of the dark matter. You have two cases. If it's a fermion, you're lucky because you only need to deal with a 68 orders of magnitude space. And if it's a boson, you have a lot more fun to have. You have more than 90 orders of magnitude. Okay, so what we know of dark matter as an elementary object is really not that much. Okay, so we have a huge freedom in picking the mass of this particle. And I told you I have little kids, so they love Dr. Seuss. I don't know if you ever heard Dr. Seuss. He speaks in rhymes. Kids love rhymes. And there's this great quote that says, "Think left and think right, and think low and think high. All the things you can think up if you only try." Okay, so that's something that dark matter model builders have to keep in mind. So mass of the dark matter, the self-interaction cross-section is the constraint we have on how much dark matter interacts. The abundance and distribution, there's one more thing that dark matter has to be, which is it has to be stable. We observe dark matter. It just cannot decay on time scales smaller than at least the age of the universe. Okay, so last requirement, I guess number 7, is it must be a stable particle where, or quasi-stable, where at least the lifetime, at least quasi-stable, so the lifetime of the dark matter has to be bigger than the age of the universe, which of course I'm going to ask you what it is in seconds. 10 to the 17 is a great number. Very good, thank you. So the universe is about 13 billion years old. Okay, we know it from the inverse of H0. So 13 billion years. There's a great way to remember how long a year is in seconds. It's pi times 10 to the 7. It's surprisingly close to pi times 10 to the 7. So let's multiply this by pi times 10 to the 7 to get seconds. So indeed, it's I'm sorry. Yeah, that's correct. So it's about 4 times 10 to the 17. Okay, 4 times 10 to the 17 seconds. Now, in fact, you can do much better than that. You can do much better than that, because if the dark matter decays in a way that leaves an imprint, then you can actually put much better constraints. What does much better quantitatively mean? Well, suppose that the dark matter decays into X-ray photons. We're going to talk a little bit about sterile neutrinos. So these are right-handed, so gauge singlet copies of neutrinos. And there's a radiative decay mode of sterile neutrino to an active neutrino and the photon, because these things have some mixing with active neutrinos, and then you can imagine that there's some loop like that. And so you can decay into an active neutrino and a photon. This is a monochromatic photon because these guys typically weigh in the keV. And so you have an X-ray photon, monochromatic X-ray photon, which looks like a line in the spectrum of X-rays. You can go after these lines, and I can tell you a lot about recent work on X-ray lines and dark matter, but we'll have time for that. The important thing is that if that's the case, from X-rays, you know that the lifetime of the dark matter has to be greater than roughly 10 to the 30 seconds. So you do better by a lot. You do better by roughly 12, 13 orders of magnitude compared to just the age of the universe. It's very easy to estimate this once you know what the X-ray sensitivity of your instruments is. So it turns out that 10 to the 30 is actually a pretty good benchmark across wavelengths. So if you look at gamma rays, so for example, you have 2 WIMPs that pair annihilate, and these are weak scale particles. So suppose they annihilate into pions, including pi zeros. Pi zeros decay to 2 photons, and so you have gamma ray photons. Well, again, if you look at how well you do in setting constraints, you have a limit on the lifetime that is, once again, about 10 to the 30 seconds. So, of course, the dark matter can decay completely invisibly, for example, into neutrinos, which are almost invisible, or into dark photons or what have you, something that we cannot detect. And in really, you're out of luck, and so this is the relevant limit. But dark matter has to be stable, at least on these scales. Very good. So now I have another 15 minutes, right? Very good. And so I will tell you a little bit about this fascinating mix of StatMech and particle and nuclear physics and general relativity. That is what we use to make quantitative predictions about the density of dark matter in the early universe. So, and again, the reason why we do this is that this cocktail works for many things. For example, recombination. Okay, recombination is essentially the story of this reaction going out of equilibrium. Okay? So that's what recombination is about. When this reaction goes out of equilibrium, photons are decoupled from electrons and protons, and there you have your CMB. Okay? And we do CMB science very, very accurately. So we know very well how this process works in the early universe, and it is through a combination of electromagnetic cross sections, it's a function of temperature, and stat mech, which tells you what, for example, the number densities of photons, a bosonic species, and say electrons, a fermionic species, are at that point, and the expansion rate of the universe. So we know how to do that very well. Similarly, we know how to do very well BBN, as I explained, and we also know how to do well neutrino decoupling, and we're actually going to do it today. So, you know, what we expect the background of neutrinos to look like in the universe. And the basic idea of how this cocktail works is this. Okay, so you have a reaction rate, or gamma, that tells you how many reactions per unit time you have of, say, the recombination or you know, whatever nuclear physics process in BBN you're interested in. And you compare this with the Hubble rate, with how fast and how old the universe is at a given point, time, or temperature. So if this is the case, you have a reaction that happens fast compared to the expansion rate of the universe. Therefore, it's very likely that that process occurs, and so that process is said to be in equilibrium. Vice versa, so this is equilibrium. If this is the case, the process is out of equilibrium. In practice, it means that the reaction happens on average never. Okay? It happens on time scales that are much longer than the age of the universe at that point. So why is this a cocktail of stat mech, particle and nuclear physics, and GR? Well, the GR part comes in here. Comes in fixing what the Hubble rate is at a given temperature. What is gamma? Well, gamma, the reaction rate, as again, you know from your particle or nuclear physics 101, a reaction rate is the product of a cross-section times a flux. That's how you define what a cross-section is how many events you have for a unit flux for a unit time. Okay, so this times the flux that I'm going to write as n times v. So here is the nuclear particle physics, and this is the stat mech. Okay? So let's refresh a little bit our stat mech and think about what n is. N, for a species that is in equilibrium, is an equilibrium number density. Okay, so what is n? For us is the equilibrium number density. It's very easy to write it down, but let me give you the asymptotics